Hello, 5th graders, and welcome to a read-aloud of today's science ebook titled Gravity, as needed for today's science lesson, Unit 4, Lesson 1, also titled Gravity. And as we can see from the intro, it tells us, what is gravity and how does it affect us? Let's read to find out. Read pages 4 through 21 in the ebook. So let's waste no time, let's get straight into it. Let's see what gravity is and how it affects us. Starting with, what is gravity? Chapter 1. If you toss a ball up, it always falls back to the ground. Rivers flow downhill. The moon always orbits or goes around the earth. What causes these events? The answer is gravity. Gravity, or gravitation, is a force that exists throughout the universe. All matter in the universe has gravitational pull. That means every bit of matter is trying to pull every other bit of matter towards it. When you walk, the earth is pulling you toward its center. At the same time, your body is trying to pull the earth toward it. But the earth does not move towards you. You move toward the center of the earth. Without gravity, you and everything else on earth would float out into space. What scientists know about gravity? There are many things about gravity that scientists still don't understand. But they do understand that gravity is a major force in the universe. As it says right here, gravity is a force. Gravity is important to the Earth and to the people on Earth. Scientists know that gravity follows certain basic laws, and they realize that those laws are the same for a baseball being thrown across a ball field as they are for the Earth orbiting around the Sun. Scientists also know that gravity causes the ocean tides and changes in weather. It gives you weight. Gravity holds your feet to the ground and keeps the air you breathe in place around Earth. Part 2. Gravity Basics. Gravity is a universal force, meaning it's all throughout the universe. In other words, it behaves the same way everywhere in the universe. Like all forces, gravity pulls objects. Billions of years ago, gravity was the force that pulled cosmic gas and dust together to form stars, planets, and moons. Even now, gravity keeps planets orbiting the sun. Our basic understanding about gravity comes from the ideas and experiments of pioneer thinkers and scientists, pioneers being the first people to do something. Thousands of years ago, the ancient Greeks wondered what caused objects to fall to the ground. After all, why didn't objects fall upward? Aristotle's ideas. So Aristotle was a very famous Greek philosopher. There's a picture of him right there. Aristotle, a Greek thinker, suggested that everything in the universe was made up of a combination of 4 things: earth, air, fire, and water, those being the 4 classical elements. He said that objects that were similar were drawn to each other. According to Aristotle, objects made of earth were attracted to the earth. These objects always fell to the ground. Fire was not made of earth, so anything made with fire rose up above the earth. Aristotle also believed that the center of the universe was the earth. The moon, planets, sun, and stars seemed to circle the earth. Aristotle did not realize that the force that made objects fall to the ground was the same force that made the moon circle the earth. So as smart as Aristotle was, having lived so long ago, even he wasn't too clear on the true nature of gravity in the universe. After all, he believed that the earth was the center of the universe, but we know that that's not the truth. So the next scientist to come along and build upon Aristotle's ideas was this man, Galileo. So what were Galileo's ideas? About 400 years ago, Galileo, an Italian astronomer, someone who studies outer space, experimented with gravity. He discovered that if it weren't for air resistance, all objects dropped from the same height will fall toward the ground with the same velocity or speed. Because of air resistance, some objects will hit the ground before other objects. For example, a heavy cannonball will land on the ground sooner when dropped than a feather will. The difference is caused by air slowing down some objects more than other objects. When gravity is the only force acting on objects, they will fall at the same speed. Galileo also said that the Earth was not the center of the universe. He said that the sun was the center. Okay, so still not accurate, but at least he knew that the sun was the center of the solar system, so that's a step closer. Galileo said that the planets went around the sun in circles. Like the earlier Greek thinkers, Galileo did not understand that the gravity he experimented with on Earth is the same force that makes the planets orbit the sun. So as much as Galileo built upon Aristotle's ideas, even he still had things he didn't understand. Scientist of significance. So a little bit more about Galileo. His full name was Galileo Galilei, born in 1564, died in 1642. Galileo Galilei was an Italian astronomer, used a telescope to see the moons of Jupiter for the first time. Galileo discovered that not every heavenly body orbits the Earth as previously thought. Galileo also carried out experiments with gravity. He dropped several cannonballs of different weights from the Leaning Tower of Pisa in Italy. His experiments disproved the popular theory that heavier objects fall faster than light ones. He saw that objects accelerate or move faster and faster as they fall to the ground. So the next scientist to come along, about 100 years later, was this man, Isaac Newton. So what were Newton's theories of gravity? In the late 1600s, Isaac Newton came up with important discoveries about gravitation. Newton understood that objects naturally move in straight lines. He realized that it took some kind of force to speed up, slow down, or change the path of an object. That is, if it's in motion. In 1687, Newton published his book, The Principia, which was one of the most influential works in physics of all time. He said that every piece of matter in the universe attracts every other piece of matter. The force of this attraction depends on the mass of both pieces of matter. If the mass of either piece of matter increases, the attraction between the two pieces of matter becomes stronger. Mass changes how much gravitational force an object has. Size has no effect. Size is simply how much space something takes up. The clue to the force of gravity is the amount of matter or mass in an object. Newton also said that when two pieces of matter are farther apart, the attraction between them is less than if they were closer together. Newton's theories of gravity were the same for all matter in the universe. A falling raindrop follows Newton's law. So does a basketball bouncing on a court, and so does a planet spinning around a star. So in other words, the force of gravity between two pieces of matter is going to be greater, first of all if the objects are larger or more massive, and also if they're closer together. Very important discoveries by Newton. Part 3. Gravity on Earth. Scientists consider gravity a weak force in the universe. After all, you hardly feel or even think about gravity when you go about your daily life. But gravity is an important force on the Earth. Gravity causes the ocean tides, water changes, and your weight, among many other things. So one very important way that gravity influences the Earth is by influencing the tides of the ocean. As it says, gravitational pull causes ocean tides on the Earth. You may have seen the tides in the ocean move in and out. The ocean tides are caused by gravitational pull. The moon has a gravitational pull on the Earth, just as the Earth has a gravitational pull on the moon. The force of the moon on Earth's ocean follows Newton's laws of gravity. The moon and Earth exert gravitational force on each other, and the force is strong enough to pull water upwards on the side of the Earth nearest the moon. The moon's gravity also pulls downward on the water on the other side of the Earth, but the downward force is weaker because that side is farther from the moon. These upward and downward forces cause high tides and low tides. The sun also has an effect on the ocean, but the sun's effect is smaller than the moon's effect because the sun is much farther away from Earth than the moon is. So in other words, the moon has a gravitational pull on the Earth, just like the Earth has a gravitational pull on the moon, and whatever side of the Earth the moon is on, the oceans there are going to be pulled up by the gravity of the moon and cause the oceans to rise. So that's what causes the tides, is the moon's gravitational pull on the oceans. So right at that part of the Earth right there, the oceans are very high. And on the other side of the Earth, the oceans are at a low tide. So gravity also affects weather, as we'll see. Gravity plays an important part in the weather. Cold air is heavier than warm air. Gravitation makes the heavier cold air sink. When cold air sinks, it takes the place of the lighter warm air under it. The warm air is forced to rise. This movement of air causes winds. Combine that with the rotation of the Earth, and the result is our weather changes. The weather may be sunny and warm. Then cold air comes in and forces the warm air up and away. The wind becomes cooler. The rising warm air forms thunderclouds that bring rain. Mass and weight. The amount of gravitational pull on an object depends on several things. One factor is the mass of the object, as we said before. Mass is how much matter an object contains, or how many atoms or molecules it contains. Large objects with a lot of mass, like planets, have a strong gravitational pull. Smaller objects have less mass, so they have a weaker gravitational pull. The Moon and the Earth are both large objects. Both have a great deal of mass. Their pull towards each other is very strong. A banana and an apple, on the other hand, are both small objects. They do not have much mass. Their gravitational pull towards each other is weak by comparison. Weight is not the same as mass, even though the two things are often confused with each other. Weight refers to the amount of force that gravity pulls on an object. Suppose you get on a bathroom scale, like that one, and you see that your weight is 85 pounds. That means the Earth's gravity is pulling on you with a force of 85 pounds. Since weight is based on gravity, your weight would change on the Moon. The Moon is much smaller than Earth, so the force of gravity is not as strong as the force of gravity on Earth. So you would weigh less on the Moon. So how much would you weigh on the surfaces of other planets in the solar system? Well, if you weighed 100 pounds on Earth, then Venus, Mars, and the Moon, all three of which are celestial bodies that are smaller than Earth, they therefore have less gravity, and you would therefore actually weigh a little bit less when you stood on the surface of them. So if you weigh 100 pounds on Earth, you would weigh 91 pounds on Venus, 37 pounds on Mars, and only 16 pounds on the Moon. So while your weight changes depending on what planet you might be standing on, your mass, however, stays the same no matter where you are. After all, once again, mass is the amount of matter in an object. So whether you're standing on the Earth or whether you're standing on the Moon, the amount of mass that makes up your body is still going to be the same. If you were an astronaut and landed on the Moon, your mass would be the same as it is on Earth. Technology link, anti-gravity machine. In the 1990s, NASA started making anti-gravity machine. Such a machine would be used to break the bonds of gravity and send astronauts on trips into space. It would also be used to place satellites in orbit around Earth. So far, the experiments have not worked. In order for a satellite to orbit Earth, the satellite must travel at just the right speed. If the satellite moves too fast, it will move away from Earth into space. If the satellite moves too slowly, it will move closer to Earth. In order for a satellite to always remain over the same point on Earth, it has to circle Earth once every 24 hours to match Earth's rotation. That's actually true about the Moon, too. That's why the Moon doesn't float out into space or fall to the Earth. It's orbiting the Earth at just the right speed to stay level. Part 4. Center of gravity. Gravity pulls on all parts of an object. However, gravity acts as if all the mass of the object is located at one point on the object. This point is called the center of gravity. Balance a yardstick on one finger. The point at the center where the yardstick balances is its center of gravity, as shown there. The center of gravity helps to explain why a figure skater can spin on the tip of her ice skates. The skater keeps her center of gravity directly above the tips. That means she is balancing right on the very tips of her skates. So a spinning figure skater balances by keeping her center of gravity over the tips of her skates. So center of gravity is just over the tips there. That's why she's able to spin so gracefully without falling over. If the center of gravity of an object is close to its bottom, or base, the object is balanced. That makes the object very hard to topple over. If the center of gravity of an object is far above its base, it has a high center of gravity. Things with a high center of gravity are easy to tip over. Things with a low center of gravity are harder to tip over. A low center of gravity is important to race cars. Race cars must be stable so they don't flip over when they speed around tight corners. There is a wide distance between the wheels of a race car. This means that the car has a wide base and the weight is down low. The race car has a low center of gravity. And part 5, acceleration. As you know, if you hold an object and let go of it, it will fall to the ground. This object will pick up speed as it falls. It falls faster and faster towards the Earth. This means that it accelerates. Gravity pulls an object and causes acceleration, meaning it moves faster and faster. Air resistance. If there were no air, gravity would cause everything that falls to accelerate downward at exactly the same rate. Without air, a feather would fall just as fast as a brick. However, air does cause resistance, or an opposing force, against objects as they fall. The air helps to slow down or hold up certain objects as they fall. Heavy objects that take up little volume or space are not affected as much by air resistance. An object of equal weight that takes up a lot of volume will experience more air resistance and be slowed down as it falls. That's why a large flat sheet of paper will fall more slowly than if that same sheet of paper were crushed into a ball and dropped. Air resistance will affect it less than when the paper was flat. Gravity is a universal force of attraction. Over the centuries, many thinkers and scientists, such as Aristotle, Galileo, and Isaac Newton, created theories and carried out experiments bringing us closer to realizing the laws that govern gravity. Today's scientists' understanding of this force that keeps our feet on the ground and the planets in orbit around the sun continues to grow. Gravity causes ocean tides, gives objects weight on Earth, and causes changes in the weather, as we saw.